Many trigonometric equations, when we're solving them, can be solved using methods from college algebra that we learned, like solving a linear equation, solving a quadratic equation, except that instead of a cute little x or y, there's going to be an entire trig function there.
Oh, y.
Huh?
Y.
You mean x. Agaga. Okay, so let's just think back to the linear methods. If I was asking you to solve this tiny little equation, what would you do to solve for x? Move the 3 to the other side, so it'd end up being 5x equal to 5, because we subtract 3 from both sides. Then what? Okay, so those are the steps you're also going to use, except that instead of x, there's a potential it will be an entire trig function. The only step after cute little linear step you have to do is that since this will be a trig function, you then go to your unit circle and give me the x values that give you that output. We practiced this last time with our inverse trig, so we're reading the unit circle backwards. The steps, if we apply that to trig functions, are number 1, to isolate the trigonometric function on one side of the equation. That is your linear steps. So you're adding, subtracting, multiplying, and dividing to isolate the x or isolate the trig function. Then you're going to go to your unit circle and you're going to find the corresponding angles on the unit circle that satisfy the given equation. The last thing you're going to do is consider any domain restrictions on the problem. I'm going to highlight that one green because I will alert you to domain restrictions by highlighting them in green. And then you're going to give me the solutions or the general solutions, which we will discuss what those mean in just a little bit. All right, so let's jump right into it. We're going to solve the equation 2 sine of theta plus 1 equal to 0. Now, before you panic, I want you to think of this as 2x plus 1 equal to 0. Do you see how these are they're the same except this says sine and this says x? Yeah. We're going to solve them at first the normal way. We're going to isolate the sine of theta the way that you would isolate the x. What would you do to solve for x right here? So that's what I'm going to do with this entire function. I'm going to subtract 1 from both sides. If it was just a regular x, what would be your next step? So I'm going to do that, except I'm going to do that with this trig function. Once I have the trig function isolated, meaning the trig function is the only thing on its side, kind of the same way the x was the only thing, this is when we go to our unit circle. Now, I forgot to draw your attention to a domain restriction. This part A says to give me the answer over the interval from 0 to 360 degrees. You get 2 pieces of information out of this green thing. Number 1, are we measuring in radians or degrees? Degrees. Great. Number 2, we're only going to give you answers between 0 and 360, which, yes, is one entire rotation around your unit circle. Now, unlike what we did last time with inverse trig and inverse cosine and inverse tangent, you don't have to restrict your circle to the 2 not intervals, what am I thinking of? Quadrants, like we did last class. So don't fold your unit circle. That's only for when it actually says sine inverse. This says regular sine, we look at the whole thing. So let's go scavenger hunting around our unit circle. Can you find me any place where the y coordinate is -1/2? So we have the angles 210 degrees. That y value is -1/2. And what was the other one? 330 degrees. Now, the next time I would get here would be an entire loop around the circle because these are going to repeat over and over and over and over and over again. However, our domain restriction, the green thing, says only one rotation between 0 and 360. So boom, we're done. Not bad, yeah? That unit circle is the key. However, if we go a little bit further and I ask you for what's called all solutions, or you may see this referred to as the general solution, I'm actually wanting an equation that tells me every single time it goes around the circle when I would arrive at 210 and 330 degrees. So question for you, all the way around a circle is how many degrees? 360. So if I'm writing a general equation for the answer 210 degrees, I would say theta is equal to 210 degrees plus every rotation after that. So you use 360 degrees to tell me a rotation, and the value k is saying multiply, or given k is an integer. Oh, we got to introduce this notation. AP Pre-Cal friends, do y'all remember this? Yeah, so this notation means that k, this number right here, is an element of the integers. This is the funky symbol for integers. The way the like R that's bolded is all real numbers. This bolded Z is integers. And it's just saying plug in the number 1 or 2 or 3 or 4 or -1, -2, -3, -4, and all of those rotations will be same. The other way we would write this, because there were two solutions, is we like literally copy paste, except we're changing the initial angle. 330 degrees plus every rotation after that, given k is an integer. I think your textbook goes back and forth on using k's and n's, but because I also teach AP Pre-Cal, I'm stuck using k's, and I can't help it. So in general, here's your little trick. Since trigonometric functions are circular, there may be many coterminal angles that would solve the equation. To write a general or all solutions, those are the words you'll see, we just did this. Theta equal to the solution you found, these are the solutions we found, plus 360 degrees times k, given k is an integer, and if we're in radians, instead of 360 degrees, you put 2 pi. Easy? That formula stays the same. You solve it finding 1 or 2 solutions on your unit circle and then slap the plus 360k on the end. That's again for what's called a general solution or all solution. Now that was almost too easy, yes? So we're going to make it a little bit harder. So now they're no longer going to be linear in form. What kind of function is this? Quadratic. Let's think how we solved quadratics in college algebra. We're always going to check for a GCF because that's just easy. Yeah. What do x squared and 4x have in common? X. So we're going to factor out the x, which means x would go in front of x plus 4. It's like reverse distribution. Do we follow? Mm-hmm. Now, when we solved quadratics and we have it in factored form, we use what's called the zero product property. You don't have to know that's why it's called. But to set each factor equal to 0. Do y'all remember doing this? So the first solution would be 0. The second solution would be -4. We're going to apply those same skills of factoring, setting them equal to 0 separately, but we're going to make it not a cute little x. We're going to make it a trig function. Same steps. So these steps, if you're wanting some words to describe what we're doing, the first thing we're doing is we are factoring the GCF of. Usually the GCF is a trig function, meaning there's like sine of theta and then sine squared of theta. They have sine of theta in common. We're factoring it on one side. We'll then set each factor equal to 0 and isolate the trigonometric function using linear methods. So then we kind of go back to the steps from the front page where we're isolating, getting the sine or cosine by themselves in one or both of the tiny equations we wrote. Then we go find the corresponding angles on the unit circle that satisfy the conditions, consider any domain restrictions, that's our green, and then write our solutions and or the general solutions depending on what it's asking for. Are we ready to see one? Sure, great, that's the spirit. In example 2, it says to solve sine of theta times tangent of theta minus sine, or what, equal to sine of theta over the interval from 0 to 360 degrees. So we're only looking on one rotation of my unit circle. We don't have to write a general solution because it doesn't ask for it. It gives me this restriction. So first things first, when we're trying to factor and using a quadratic, we always set the quadratic equal to 0. So if I have sine of theta, tangent of theta, I'm going to move that sine of theta to the other side of the equal sign so that everything is on one side and it's set equal to 0. The zero product property can only be used when it's set equal to 0. Do you see how the first term and the second term both have sine? We're going to factor out sine of theta. That means I'm taking the sine of theta away from each factor and seeing what's left over. Well, if I take sine of theta out of sine theta, tangent theta, what's left? Tangent of theta. And And if I take sine of theta out of sine of theta, what's left? 1. Okay, can I just say that on the chapter 5 test, since I all finally graded it all, the number of times y'all did like sine over sine, and you're like, canceled, and then didn't put a 1 in that spot was crazy. When it cancels tops and bottoms, it becomes 1. If it cancels, like combining like terms cancel, that's when it disappears. But tops and bottoms cancel, it becomes 1. Okay. Sorry, I digress. Equal to 0. Well, now it's factored, so I can set each factor equal to 0. So the first thing equal to 0, and the second thing equal to 0. For this first equation I wrote, sine of theta is straight up by itself, so it's already isolated. But in the second equation that I wrote, is that tangent of theta isolated? No. What do I do to isolate it? Add 1 to the other side so that tangent is straight up by itself. So now it is isolated. We've done that second step. The third step says to go to your unit circle and find the values of theta, find the angles that give you 0. So for the first one, where is the second coordinate equal to 0? Okay, that's a good point. Are we using degrees or radians here? Degrees, because of the way that it asks the domain restriction. There should be 2 places where this happens. 0 degrees and 180 degrees. So we have 2 solutions here. We have 0 degrees and 180 degrees. Why would I not answer 360 degrees? True, it is where we started, and look at my domain restriction. Is 360 included? No, that parentheses means right up to 360, but don't include 360. So we can't answer that. Now we go back and look at our unit circle for all the places where tangent would be equal to 1, positive 1 specifically. 45 degrees, there should be 1 more space. Where else would tangent be positive? Yeah, the third quadrant is the T quadrant. And if 45 degrees is the pink line in the third quadrant is 135 degrees. So I have 4 solutions to this equation. 0, 180, 45, and 135. Wait, not 135. I just totally believed you. That's quadrant 2. 225. Here I was just believing you. I do too, yeah, it's fine. We've been there. Sorry. That's the one that actually is in quadrant 3. Oops. Questions, comments, concerns? Okay. So if we keep increasing our algebra skills, but as we add in our trig functions, what did we do back in college algebra to solve something like this? We factored it. You're thinking quadratic formula? We'll get there. We can factor this. Remember when we did factoring, a lot of you use an X puzzle to factor, which is fine, but I like to guess and check. We set this up as X parentheses and then X parentheses. We look at the last number, the C value, and we think, what are the numbers that multiply to 8 and add to 6? 4 and 2. And they're both positive because there's only plus signs. Okay, great. Now that it's factored, we'd use the zero product property, and bing, bang, boom, we'd get x equal to -4 and x equal to -2. Does that sound familiar? We're going to do the same thing, but with a trig function. However, using this with trig functions for a lot of people is not something you visually see very well. So we're going to make it easier by using what's called U substitution. So we're going to force it to be, instead of a trig function, a function with respect to u. We're going to switch out all the trig to the letter u, and then using the letter u, we're going to factor the quadratic function. It will look very much like this, very college algebra style. We can do that. And then we're going to substitute our trig back into the function for u. So we're just being like, just kidding, put that to the side, plug in a u, do some stuff with u, and then say thank you very much, put the trig function back. After that, you set each factor equal to 0 and isolate. Oh, look, these are the same steps as before. We look at the unit circle, we consider any domain restrictions, and then we write a general solution if we need it. If you do not need to do U substitution, because you can look at the trig equation without having to switch it to U's, go for it. But I highly recommend using U substitution. Why the letter U, you ask? I actually don't know. It's just the way we do it. Probably because X and Y are already measuring things, and so they're like, what other letter can we use? They used a U, yes. Yeah. No, not next class. Next class there's a quiz, but it's an activity that counts as a quiz grade. But then the class after that, yes.
So Friday we can have an exam.
Yes. Look, you have 2 whole days that you're sitting in a STAR testing room doing nothing. You can study for my test. You got it.
This is a very short section.
It is. I'm important. I'm going to pull a selfish on that one and say you should do my class. Okay, here we go. We're going to solve tangent squared of x plus tangent of x minus 2 equal to 0 on the interval from 0 to 2 pi. Okay. So 2 things. Because this is between 0 and 2 pi, are we measuring in degrees or radians? Radians. And will we give a general solution? No, because it tells me only to answer on 1 rotation of the unit circle. Great. That looks complicated. I see some stuff that's squared, some stuff that's not squared, and a regular number, which means this is how we want to do U substitution. We're going to put the phrase, let U equal to tangent of x. We have to define what we're doing for this U substitution. We're going to let every tangent of x be represented by U. So then I can take the equation I was given and rewrite it, and instead of tangent squared of x, I can write U squared. And instead of tangent of x, I can write U. And then the negative 2, it doesn't change. That right there is the U sub version of this equation. This will be easier for your brain to factor because we can factor this the way we just did on the other side. We set up U and U. What are the things that multiply to negative 2 and add to positive 1? Let me back up. What are the things that multiply to 2? 2 and 1, and then yes, we want a positive 2 and a negative 1. Ta-da! Then we're going to undo the U substitution. The U is just basically a placeholder for us to make it easier for ourselves. We're then going to come back, and we're going to resubstitute back in our tangent of x. So anywhere there was a U, we put back the tangent of x. That's a U substitution. So then we can take each factor and set it equal to 0 and solve them independently. In that first equation we wrote, tangent of x plus 2 equal to 0. Is tangent of x isolated? We subtract 2 from both sides. And now that it's isolated, we have to think to ourselves, what are the values of tangent that would give me negative 2? And before we go there, let's solve the other one. Let's isolate the other one because we'll come back to that step after lunch. What will we do on the other equation to isolate tangent? Add 1. Okay, after lunch, we'll discuss how to answer these questions, but we have successfully isolated the trig function using U substitution. All right, now that we're back, well, let's start with the easier one. So we're going to solve this side first. Tangent of x equal to 1 is something we can answer with the unit circle. And I think we've already done that technically today. What are the angles that would solve this, that you could plug in to get 1 for tangent? Ooh, are we measuring in degrees? Pi over 4 and 5 pi over 4. So we technically already found that one on a unit circle. Great, awesome. Is the number negative 2 on your unit circle? No, but so we have to think for a second. Is the number negative 2 in the range of tangent? The correct answer is yes. The range of tangent is from negative infinity to infinity. If that had been sine or cosine, sine and cosine range only goes from negative 1 to 1, so that would not work. However, since this is in the range of tangent, we have to have a way to answer this question. So we're going to turn to our handy-dandy calculator. In your calculator, first things first, we're measuring in what in this problem? Radian. So change your calculator into radian mode, in case it's not. And we need to figure out what value of x would give you negative 2, because it's not something we can answer with the unit circle. We're going to have to go back to what we did last class and use inverse operations to do this. What is technically the inverse operation of tangent? That's a reciprocal. What is the Inverse of tangent. Arctangent or inverse tangent. Very good. So we are, in our calculator, going to compute inverse tangent of -2. So if we do inverse tangent of -2, what do you get? Cool. So here's the problem with just this answer. Number one, there should be two places, right? Because most of these things have two solutions. So we need to figure out where the other solution is. And in fact, this first solution is not even in the domain restriction that I'm working with. Is -1 between 0 and 2 pi? No. So we actually have to adjust this so that we are within the correct window. For tangent, you're going to add pi to these numbers. Why pi? Because the period of the tangent function is pi. If it was sine or cosine, you'd be adding 2 pi because the period of sine and cosine is 2 pi. But what I want you to do right here is I want you to add pi. Use the pi button. What do you get when you add pi? 2.0344. And then I want you to add pi one more time. So we added both pi and we added 2 pi, so we have our second answer. What's the second time if you add pi one more time? Boom. Those are your other two. So we have our 4 solutions here. Again, we had to do this because -2 is not on my unit circle, but it is within the range of tangent. So we go to inverse tangent, which we learned about last time, throw that into a calculator, and because this was outside of the domain restriction, you have to force it into the domain restriction. So you add pi to get the first one and add another pi to get the second one. Are you ready to try another one? This one gives you a hint in the title. It says example 4, solving a trigonometric equation using the quadratic formula. Whoa. What's the quadratic formula? X equal, this is from college algebra.
Y equals mx plus b.
Love that one, but no. It starts with x equals. Oh. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. It's Pop Goes the Weasel, but it is.
No, Miss, we learned the negative boy.
Yeah, I don't know that little. I know Mr. Hoddle teaches that, or somebody else. The square boy, 4 awesome chicks. I don't remember that story, but I know it in song. You know that. The quadratic formula is the fail-safe method to always solve a quadratic equation. So this problem, hint, is going to need us to use this. Let me tell you why. If we look at this problem, it is cotangent times cotangent of x plus 3 equal to 1. If it was set equal to 0, we'd be home free. But it's set equal to 1, so we have a problem. Also, please notice that it says all solutions. Does that mean we're going to write a general solution? Yes. So first things first, let's start to solve. We're going to have to distribute this cotangent to both pieces. This is going to end up being cotangent squared of x plus 3 times cotangent of x equal to 1. And since I now realize that it's a quadratic, we're going to have to set it equal to 0, which means I subtract 1 from both sides. This is where your brain would be like, there's way too much going on. So we do some u substitution to simplify. We're going to let u be equal to what? Cotangent of x. So this becomes u squared plus 3u minus 1 equal to 0. If we tried to factor this, what are the things that multiply to -1? 1 and 1, yes? Is there any way to make 3 out of 1 and 1? Rip. Okay, so we have to do something different. This is where that quadratic formula comes in. In that quadratic formula, the a is equal to 1, the b is equal to 3, and the c is equal to -1. Do we see how I got those 3 numbers? We're going to plug them in. This formula would say u equal negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Do we follow how I did that? I'll give you a second to catch up because I know I wrote it fast. It's a good point. Let's go ahead and simplify that. Oh my gosh, the word just escaped me. Starts with a D. It's whatever's underneath here.
Denominator?
No, not the denominator. The no. Determinant. There it is.
Matt.
All right. But Joseph already said it, so we're going to do the stuff from underneath the square root, which is 3 squared. What's 3 squared?
9.
9. And you have negative 4 times 1 times negative 1.
That's positive.
So we're doing 9 plus 4. What does that become? 13. Can you take the square root of 13? No. And then 2 times 1 in the bottom, we could just do 2. Cool. So that is 2 numbers, correct?
Yeah.
We have the positive version, and we have the negative version. Ooh, notice we're still in U substitution. We got to undo this, which means now we put back the cotangent. Cotangent of x is going to be equal to negative 3 plus or minus the square root of 13 over 2. The answer is simple to this. Can you find negative 3 plus square root of 13 over 2 on your unit circle? Is that a number you recognize from your unit circle?
No.
No, so what are we going to use to solve this problem? Great. Now, we have to use inverse trigonometry to do this.
Okay.
What is the inverse of cotangent? Inverse cotangent. So we're going to do cotangent inverse of negative 3 plus or minus square root 13 over 2. X is by itself. We're good to go. We just got to shove that in a calculator. Uh-oh, can you shove that in a calculator? No, did we remember what we did last class when we were taking inverse cotangent? No, you're thinking stats.
Can I look at it?
Yeah, look back. Look back at what we did last class when it wanted us to do inverse cotangent. Something about a fraction, okay. There's a lot that was just said.
1 over.
Okay, but still cotangent?
No.
Tangent. So remember, since these are reciprocals, their inverses are still reciprocals. So we can do the reciprocal of what was inside the cotangent function for tangent inverse. Yes?
So it's just tangent inverse?
Yes. Now I know theoretically, if this was your final answer, I'd be like, please rationalize the denominator. But we are just using this number to get a final answer. So we just have to throw this in a calculator. Okay? If we do the positive version first, we're going to go to our calculators and do second tangent, which is tangent inverse, of the fraction 2 over negative 3 plus square root 13. Not plus and minus, just pick one. What did you guys get there? So we'll round that to 8. And then we have to go back, do the same thing. To shorten your life, go up with your calculator and highlight what you've typed in. It will retype it. Scoot over to the plus sign, change it to a minus. Not a negative, but a minus. And then press enter. Say that again.
That's stupid. Okay.
I got something different, and I think I know why, but let me just make sure that I'm not crazy before I say something incorrect. You got negative 0.294. Great. That's a good start. I'm going to write that number down just so we see it.
I'm gonna add pi to this.
Ooh, great idea. Because is that on a normal unit circle from 0 to 360?
No.
No, so we're going to add pi. So plus pi to that, what do we get?
2.8476.
2.8476. Just so you later will know where this came from, right? Those are our two solutions for x. Unfortunately, this question asks for all solutions, so we do need to write a general solution, but it's like not much more work. You already have the numbers you found. The general solution here is x equal to the number you found plus pi times k, and the number you found plus pi times k.
We don't have to write that k easy.
Don't call it k easy. K is an element of the integers, but I get what you mean. It does need to be there. I just was writing it once because I got lazy. Now, I want you to look back at the box that we have on the notes that discusses solving these equations, because the formula I just used is different, and I want to talk about why. So when you get it written down, flip back over there for a second to the box that talks about the general equations. That formula, does it have pi in it?
Yeah. It's 2 pi k.
It's 2 pi k. It's 2 pi because the period of sine and cosine is 2 pi. What's the period of tangent? Pi. So for tangent, you only need pi, not 2 pi. For sine and cosine, you need 2 pi, because that's the period of the sine and cosine function. That one was pretty gnarly, but honestly, you know how to use the quadratic formula. You've done that before for me. I totally get it. So we've done some linear methods. We've done some quadratic methods. You will also potentially see some methods of solving that require chapter 5. We're going to use identities to do the same thing. Huh? No. Well, maybe. I'll help you with the formula you need. So the main idea here is that if you know that it didn't work quadratic, it doesn't really work any way else, you may have to use an identity to solve an equation. So the first step is to determine which identity would relate the trigonometric functions to each other. Meaning, if you have like a cosine and a secant, those are related by the reciprocal identity. So you may use that to make it easier to solve. Then you're going to apply the arithmetic needed to utilize that identity, solve using whichever method previously applies to the problem. Again, consider any domain restrictions. And last but not least, you're going to have to check for any check for what? I don't have a number 5 on my... I'm assuming this is the word extraneous. The ones that when you plug them back in don't make sense.
Oh.
And then write the solutions and or the general solutions. Because you're manipulating this problem a lot, you do want to make sure you didn't change it too much, which is why you check for extraneous solutions. So let me give you a training wheels example here. It says to solve tangent of x plus square root 3 equal to secant of x on the interval from 0 to 2 pi. Degrees or radians? Do I need to write a general equation? No. There is only one trigonometric identity that relates tangent to secant. And in chapter 5, you would have looked at that identity list, and you would see that 1 plus tangent squared of x will be equal to secant squared of x. Since they would not have any common terms, since they do not subtract away, we're going to have to use an identity to get this equation to all be in terms of one trig function. Here's what I notice. I notice that secant square is squared over here, yeah? Is secant squared here?
No.
Yikes, we have to square it. But what you do to one side, you have to do to the other. So if we're working on this, we're going to square both sides. So we're going to do tangent of x plus square root 3 squared equal to secant squared of x, because we're squaring both sides, yes? You might want to show the work to FOIL this, which means you're doing tangent of x times tangent of x. You're doing tangent of x times square root 3, which is tangent or square root of 3 tangent of x. Then you're doing square root of 3 times tangent of x, same thing. And then square root of 3 times square root of 3, which is 3. Let's simplify some things. What do you notice is happening in the center here? It's the same thing. So I could just write that as like double. So tangent squared of x plus 2 square root 3 tangent of x's plus 3 equal to, and then I need to take a moment and I need to use the identity that I've identified earlier. What is secant squared equal to? 1 plus tangent squared of x. So I can substitute that in. That is the identity that we recognized at the beginning that relates these two trig functions to each other. It's the only way they're related to each other. Hang on with me because this problem gets really simple in like one step. I need to move everything to one side. I see squares, right? So I need to be setting things equal to 0.
Yeah.
How do I move this to the other side? So what happens over here? They cancel. And this is adding, subtracting cancel, so it straight up cancels and actually disappears.
Yay.
How do I get this 1 to go away from this side? I subtract it. So what I have left is 2 square root of 3 tangent of x plus 2 equal to 0. We subtract tangent squared of x on both sides. Nicely, that cancels it out. We subtract 1 on both sides. We start to solve this. Now it's a linear function, which means we're going to subtract 2 from both sides. What are we going to divide by?
2 root 3.
2 root 3. The whole thing, because that's just numbers in front of tangent of x. Remember, our goal when it was linear was to get tangent of x by itself. Do you notice something here? We will have to rationalize, but what do you notice is on top and bottom here?
Oh, 2, 2.
These cancel, they become 1. So this becomes -1 over square root 3, which, yes, I hate that. How would you really rewrite this? But it's negative, so negative. Is that a number you recognize from the unit circle? Yes. If you flip your unit circles over, that's where we have all of the tangent information. What angle gives me -3 square root? Okay, let me rephrase. What angle gives me square root 3 over 3? But if I want it to be negative, what's the negative versions of that angle?
The negative version?
Yeah, for tangent.
Okay.
5 pi over 6.
5 pi over 6, okay.
And 11 pi over 6.
Huzzah!
Yay.
The only problem is we did an identity. So we changed part of this problem pretty substantially. So we need to double check that one of these answers is not extraneous, is not extra. It's a really good thing we have our calculators. This will make this easier. You're going to come to the side and you're going to do your check. You're going to plug in the first x value you found to the original equation, which was tangent of x plus square root 3 equal to secant of x. In your calculator, you'll type this in. Make sure it's in radians. You press enter. You type this in. You press enter. If those numbers are not the same number, this is an extraneous solution.
What are you getting at? It's 1 over sine, right?
Yes, 1 over cosine, sorry.
1 over cosine?
Mm-hmm.
And then we have to do the same thing with the next one.
Correct. So tangent of 5 pi over 6 plus square root 3, and then secant of 5 pi over 6. Do your calculators spit out the same number for both? No. So we panic. We probably check it one more time, make sure we're in radian mode, all those things. But no, these are actually not equal to each other. So can we use 5 pi over 6 as an answer? We would get rid of it. And because we're nervous, we would check the other one. We would check tangent of 11 pi over 6 plus square root 3 and see if that is equal to secant of 11 pi over 6. So same vibe. You check each side and make sure they're actually equal. And if they are, you leave that one as your answer. If they're not, this has no solution.
Oh, I did that.
Does this one come out to the same number? It should.
It is not.
Yeah, just
Oh wait, I did that one.
whatever cosine of 11 pi over 6 is 69.
Mm-hmm.
Yeah, it,
Are you closing? Okay, this is a good point. Are you closing a parentheses after tangent 11 pi over 6, close parentheses, plus square root 3?
Oh no.
Mm. Close your parentheses. But yes, this one works, yeah? That means we leave 11 pi over 6 as part of our answer.
Okay.
They were the same number, he just said they were different.
Joseph.
I was paying attention. I was looking at the wrong number.
These are, I will tell you, a little bit more challenging because you have to get creative with the chapter 5 information on how to relate one side of the equation to the other. Last example for today, it says, a basic component of music is called pure tone. The graph in the figure models the sinusoidal pressure, y equal to P, in pounds per square foot from a pure tone at time t seconds. The frequency of a pure tone is often measured in hertz. 1 hertz is equal to 1 cycle per second and is abbreviated Hz. What is the frequency F, mine is all blurry, in hertz of the pure tone shown in the graph? Okay, we need to figure out the frequency. Frequency is the number of cycles per second. So we want to figure out the cycles per second. In the image that you have here, looking from start to finish, how many full cycles of this sine function do you have? So 1, 2, 3, 4, 5, 6. So we have 6 cycles in how many seconds?
0.04.
Great. A hertz is measured in 1 second. So if 6 cycles happen in 0.04 seconds, how many cycles will happen in 1 second?
11.
What is the, I've written it this way on purpose. What is this setup called? It starts with a P. It rhymes, it sounds like, no, there's no word that it rhymes with. It starts with a proportion. A proportion.
Wow.
It sure is the butterfly method. Cross multiply and divide. So we're going to cross multiply and divide, but we can do part of this in our head. When we cross multiply, this would be 0.04x. This would be what?
6.
So to solve for x, what would you do? So 6 divided by 0.04,
Is 150.
150 hertz. That's the frequency of this pure tone. The time for the tone to produce 1 complete cycle is called the period. We know that information. Approximate the period t in seconds of the pure tone. My friends, don't overthink this. How are frequency and period related?
Somehow.
They're inverses of each other. Frequency is 1 over the period, therefore a period is 1 over the frequency.
Yeah.
So the period here would be 1 over the frequency. What frequency did we just find?
The 150.
150. So the period of this function is 1 over 150, which if you trust me and throw that in a calculator, it is approximately 0.006, a bunch of repeats, seconds. An equation for the graph is y equal to 0.004 sine times 300 pi x. Use a calculator, estimate all solutions of the equations that make y equal to 0.004 over the interval from 0 to 0.2. we are asking, basically, where the outputs would be equal to 0.04. This is 0.04.
Yeah.
How many times in this image does our graph touch that particular level? 6. The problem is, it's only asking for me to check between 0 and 0.2, which is to here. How many times does it actually touch in that interval? 3. I need to know those 3 points. We're going to use our calculator for this.
Okay.
You're going to go to y equals, and in y1 you're going to type the equation that it gives you, 0.004 times the sine of 300 pi times x. And in y2, you're going to type 0.004. Sorry. It will, on your screen, if you change your window to approximate the window shown on my your notes, it will show. Do y'all need me to show you how to do this part?
Yeah.
I think so.
Just changing the window.
Yeah, changing the window. I'm going to show you on my actual calculator over here, so that you can actually see the buttons I'm pressing. Okay, so I'm going to go to y equals. Well, first of all, I'm checking I'm in radians. I am. Okay, I'm going to go to y equals. I'm going to type in that equation, 0.004 times the sine of 300 pi times x, and then 0.004 is in y2. If I press graph right now, nothing important shows up to me because I need to go to the window and I need to change my window settings. The domain restriction is from 0 to 0.002. That's too many O's. 0.02. The maximum value that you see on the notes right now, I can't show you both. The maximum value for the y's is 0.006. I'm looking on the y-axis there. What's the minimum value?
Negative.
So if I press graph, I'm going to see this wave zoomed in to exactly the places I want. Just like we saw on our paper, how many times does this cross? 3. Instead of saying how many times does it cross, what's a word I can use to talk about the crossing? It starts with an I. Intersection. In the calculate menu of your graph, second trace, option 5 is the intersection. You do have to move the little turtle close to where you're looking. So it says go to the first curve, so you're going to go close to the intersection we care about first, at the first intersection. Once you're close, the little turtle's flashing over the intersection. You press enter 3 times. Boom, boom, boom. And it's going to give you the intersection point. That value x, 0.00167, is your first solution here. 0.00167. But there are 3 more solutions, so we repeat those steps. How did I get to intersection?
Move the turtle.
Well, before I move the turtle, I have to press something. Second, yeah, calc or trace. Option 5. Now I move the turtle to the right, boop, 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 until it gets close. Once it's close, enter 3 times. 1, 2, 3. It changes to the word intersection, and there's your second answer, which is 0.0083. I do all of that one more time. Second trace 5. Move the turtle over. Enter, enter, enter. And our last intersection point is 0.015. I'm just writing the solutions down. Sorry, so you can see what I'm doing. I just literally wrote the solutions that we got from the screen.
Can you go back?
Yes. So as long as you know how to manipulate the window, bless you, to give you a trig equation that makes sense, you can use your calculator to solve a lot of these. Now, if it asks for an exact answer, you're going to go back to your unit circle, though, because those give you exact answers. But real-world scenarios can also be solved for trig functions.